again, Michael.
Morning.
How you doing?
Good. How are you?
All right. I'm set up and ready to roll. We're just going to intro to the lab. Do you have any questions before we get started?
No, sir.
All right. This one, I have a video that I made back in 2020, I think it was, explaining it all. So I'm going to let that do the lion's share. I just want to warn you that when you click on the video link, it will require the password, which you'll see in the title. It's some weird assortment of letters and symbols or whatever. But you click on that, and that opens up another window, and then you type in the password, and then that opens the video, but you literally have to wait for like a minute and 20 before any audio starts. It just says Billy Younger or William Younger across the top. So I apologize for that. There's a couple spots where I reverse X and Y, like I mentioned that the slope is rise over run, which is the change in Y over change in X. But then I literally say it backwards. I say change in X over change in Y. So just watch out for that little stuff, but know that sometimes those errors happen. Let me go ahead and share my screen and show you exactly what's going on with the lab this week. So let's do it right here. All right, so this is the lab module for this week. I've already got the lab set up for next lab, which is on Thursday, and you can see we're going to do linear graphing 2 on Thursday. Y'all just can't see that yet because it's not been published. But here you see linear graphing 1. This is the video that I told you about, and this is the password 3, capital E, 5, at symbol, capital O, capital E, percent symbol 9. That's the actual password. When you click on it, it'll then ask you to enter the password, and then you watch the video. And like I said, it's going to for some reason, I didn't edit it down, so it takes about an extra minute and 25, minute and 50 seconds before anything even happens. So just pay close attention to that. In other words, skip over that part and know that you don't have to watch that thing. Even though the whole video, by the way, is about 25 minutes. So it does a full, fairly exhaustive explanation of the lab in its entirety. So it tells you exactly what you're supposed to do, all that good stuff. So definitely watch it. That gives you the background of the lab. It even tells you, for instance, like Enrico Fermi, I have his book that was his introduction to nuclear physics that he gave to the people at the Manhattan Project. Basically, it was just an impromptu course on nuclear physics as we were learning it in real time, and someone copied the notes down and now they're published by the University of Chicago. So I've got information in there that I point out about Enrico Fermi because he was discovering something completely new. He just applied the scientific method repeatedly with simple things like curve fitting. So it's a really good example to use for this because that's sort of the beginnings of science is when you not only start to conjure up a potential cause or even just a model that you can use to represent a physical phenomenon, to represent a physical phenomenon. When you start to actually say, okay, well, here's a particular variable of interest about this phenomena, and here's another variable of interest about that phenomena. How are those two related? One of which is the dependent variable, and the other which is the independent variable. So we normally graph the dependent variable on the vertical axis up and down, and the independent variable is the one that you just choose, and that's on the horizontal axis. But once you choose that independent variable, it's automatically locked in for a specific dependent variable. So that's what we put on the vertical axis. Then you can obviously make a model, and that model might give an equation representation between those two variables, like variable 1 raised to the 3.5 power is equal to 4.72 times variable 2 to the 3 power plus some random constant or something like that. That could literally be what it is. You just had to figure out, that weird those weird exponents that I came up with. Well, that's what this linear graphing 1 and 2 labs are teaching you how to do, is uh, how we can assess a functional relationship between a dependent variable and an independent variable. How does the dependent variable depend on the independent variable? So again, like I said, that's the beginnings of science often. Hopefully you're, I'm a theorist, so I say I'm a theorist. I'm not a practicing scientist. I'm not actually doing work to further our knowledge, so I can't claim that. I am a teacher, right? But I'm teaching physics, and one of the fundamental ideas of physics is you have to come up with some kind of model or something like that. As a theorist, we prefer to make up a model a priori before we have any experimental data and then predict the results. And then we do an experiment, and lo and behold, hopefully we find that the results are a perfect match of our model. So that's sort of what you're doing here. This document right here, Lab 5 Graphing 1 Addendum, that's the document that tells you how to make this into a face-to-face lab. But to be honest with you, the video is telling you that to some extent too, because you're ultimately, as you probably guessed by now, you're going to turn in your lab here like you always do. But in order to conduct the lab, you're going to need to see a video of some of the experimental procedure, and that's what ball on incline carpet is, and that's what Atwood machine here is. So these are both videos that you should be able to click on, and from those you can basically see how we got the data that we got and that sort of stuff. So all you're going to do, as I said, is you're going to watch this video. Like I said, it might take 25 minutes. Again, you can cut out the first minute, minute and a half, or almost 2 minutes, I think it was, because that's nothing. Uh, be mindful that obviously I'm like always when you speak contemporaneously or extemporaneously, sorry about that. When you speak that way, you're bound to make mistakes. So there's little errors, like I found that I said the change in y over the change in x when I actually detailed the formula. I said x2 minus x1 over y2 minus y1 when I really meant y2 minus y1 over x2 minus x1. So little stuff like that's always going to happen. But as I said, this is the lab document. They show it in this video too, and then this is the addendum. And I want to point out exactly what the addendum says because, again, that's the key point. View the video that shows how the data was gathered. You will complete the lab precisely as explained in the lab book, but using the data below for the ball rolling on the cart and the Atwood machine. So here's the data. What we were doing is distance versus time, or no, I think we did distance versus length. So basically, we had a meter stick that we had basically married to another meter stick. So we put the two meter sticks going like this, and with a little gap in the middle, we put a little tape to hold those two meter sticks together, and that made a little gap, and that little chime, if you will, is a slot for a ball to roll down. Now we take the end of that meter stick, there's two meter sticks that form a ramp, and we put one in like in a chair or something, so it's up high, and then the other end lands on a rough rug. And then what you do is you allow the ball to roll down the incline, and then it rolls some distance across the rug. And what we're trying to figure out is what distance across the rug is the result for a given distance up along the incline plane. So this is our data. You can see for a certain distance, we did 20.8 centimeters, and then the second trial was 20.8 centimeters, and the third trial was 20.8 centimeters. So what that meant is when we used the meter stick length of 10 centimeters for the height at which we released the ball, it went in the first trial 20.8 centimeters across the carpet, then 20.8 centimeters across the carpet in the second try, and then 20.8 centimeters across the carpet in the third try. So we'll take the average of those, and that'll represent our basically our y value for the given x equals 10 centimeters. Okay. Now, you can plot all this in meters and meters instead of centimeters and centimeters if you want, but you could technically do it in centimeters as well. Just listen to whatever the lab report document tells you. Then when we did 15 centimeters on the actual meter stick, we found 30.1, 30.1, 30.2, so on and so forth. So that's the data. That's what you'll be putting in the actual lab report write-up that I gave you, the Word document. And then you're going to do the Atwood machine, and the Atwood machine starts off with, a big mass that the manual tells you about on one side and just a hanger like on the other side. And what you end up doing is take the mass off of one hanger and put it on the other hanger, and then look at the acceleration that you get for that difference in mass. So the difference in mass is really what we're plotting on one axis and the acceleration on the other axis. The difference in mass means if I have like 5 grams on one side and 15 grams on the other, the difference in mass between the two sides would be 15 grams minus 5, which is 10 grams. So that's what we're talking about here with the difference in mass. And then we do three observations with that difference in mass, and we get an acceleration of 1.306, 1.296, and 1.293. We take the average of those, and that's going to represent the y part of our variable for the given x part of our variable, which is 0.110. So you're going to do that, as I said, and that's all you really have to do to complete this lab is using these pieces of data, or these two sets of data. So now I'm going to go back to the module, and I don't think I have a list of comments for this lab, but if I do, I will put them here. They're just not there yet. But as you know, once you're finished filling in the actual document, remember you only fill it in with a color font that's other than black. Of course, handwritten is fine too. This is one though, and I just want to double check, make sure I hadn't made you guys do this before. Yeah, I didn't think I did. It's been such a short period of time since last semester, I couldn't even remember which labs we've done.
I do have a
But
question.
what's that, Michael?
I do have a question. So on
Yeah.
the graphs, are you required that they're done on Excel or they could be hand drawn?
Ah, so that's actually exactly what I was getting ready to talk about.
Okay,
This
cool, cool.
lab, this lab, you're going to do exactly one by hand because
Okay.
I need everybody to have that experience. And if you have your own graph paper, that would be better because there's a printed graph page that's in the end of the manual, and you can do it right with that by printing that paper out. But if you have graph paper where the little squares go from all the way from the left edge to the right edge and always from the top edge to the bottom edge, or at least come closer, that would be better to use. But the big part is you need to, first off, figure out which has the largest range of data. So, for instance, if you're plotting distance versus length, like we did on that first set of data we were looking at, if we found the smallest distance to the largest distance was one number, and then we said the smallest length to the other to the largest length was another number, the range between those that's largest should probably be the one that goes on the vertical axis of the paper. So it might force it to be in landscape mode because that might be, in fact, your independent variable. And then the
Okay.
other one that has a smaller range, you're going to fit that in the shorter edge of the paper. And not only that, you're going to try to choose a scale so that you're not having your graph like all over here in the corner of the paper that's this big. You want you want your leftmost data point to be at the leftmost edge of the paper as close as possible. Your rightmost data point to be as close to the rightmost edge of the paper. Same thing with your lowest data point being closest to the bottom and your highest data point being closest to the top. So you got
So
to
just go
play a
from
little bit.
0, just center mass.
Yeah, sort of
Okay.
your yeah, you just want to make sure you're trying to use as much of the paper as possible. So literally what I often do when I go to grade this is I look and I say, okay, here's an 8.5 by 11 sheet of paper. 10 inches or 10% of 11 inches is 1.1 inches. If I find that you have 1.1 inches or more of empty space, then I start taking points off because you didn't make use of even 90%
I see.
of the height. And then I do the same thing for the width, which is 8.5. So 10% of that would be 0.85 inches. So if there's more than a 0.585 inch gap between the right side and the left side and the edge of the data, then you haven't used it appropriate either. So I just want you to make sure you sort of maximize that. Uh, it's a little bit about understanding numbers, making up scales, optimizing data so that you can use it. It's just a mental exercise that I think is extremely important that everybody go through, even if you're not going to be an experimentalist, and even if from now on we're not going to graph things like that. It's just a mathematical thought process that's really valuable to you as a student of science. So you will have to make that graph, and the other ones you can use just with Excel, by the way. Okay.
Okay.
And that's where, from here on out, that first one you're going to do, and it tells you in that video, it says, okay, you're going to, maximize the graph space. You're going to draw your vertical axis. You're going to draw your horizontal axis. Using that scale, you're going to place the data points. And then they even recommend you use a clear scale. That means a ruler that you can see through, or even just really thin paper so you can get a straight edge while seeing through it. The advantage being that you can lay this on top of the graph with the data points and slowly move it and still see the data points through the clear plastic ruler because that allows you to find a line that looks like the best fit for all the points. What you're trying to do is find one line that sort of hits all the points equally well. So in principle, you might have a stray point that's quite a bit further away than the other points from the line that you chose. But in general, if one point is 2 centimeters away, the next point is going to be about 2 centimeters away, maybe on the opposite side of the line, and 2 centimeters for the next one, 2 centimeters for the next one, so on and so forth. If you've got it sort of sandwiched like that perfectly, then that's a pretty good eye estimate of what we call a least squares fit. But from here on out, once you've done that one by hand, and you'll be surprised, you're going to go back and then do it with Excel and do a least squares fit. So that's the mathematically precise way of doing it. And you're going to discover that your curve fit that you did by hand is really not that bad. So that's part of the exercise as well. And that's it. That's what you got to do. Again, if I can find comments on linear graphing one, I'll put that here just above linear graphing one turn-in area. This, as always, is due a week from today, but at 11:59 p.m. So a week from today is the 16th. So you have to have it at 11:59. Oh, I do need to say also that a week from today, I'm going to have to do the lab at a time other than 8 a.m. I might record it the day before, or I might record it after. I have I'm taking a friend to a doctor's appointment, and it's a pretty serious thing, so I want to make sure I get that done, and I won't be able to meet class, so I'll make sure your lab is done a week from today, uh, either the day before or the day of, and posted. I just won't have the 8 to 9 slot available. Any questions for that, Michael?
No, sir.
All right. Let me know. And remember the easiest way, especially when you're dealing with labs, the easiest way to contact me if you have any problems is by text. That's the way I get it the easiest because I get so many emails. I have a spam filter and all that stuff, but I get so many emails. I sometimes just miss a student or two in the pile of all the emails I got. So that's why the text messages works a little more conveniently for me if you need.
Okay.
All right. And let me know if you need anything at all. We're actually done. You're free to go. And you're also, this is sort of an office hour too for you. So if you have any questions about course material, tests, or course practices, or just any homework or online practice test problems or anything that you had, just let me know. I can answer those here now too.
Yeah, it was what was that book called? Because I started reading American Prometheus. I just watched Oppenheimer. It's
Yeah,
like,
that's great. That's yeah. That book, American Prometheus, was friggin' awesome, and that's by Kay Bird, and I forgot the other author's name. But the book that I was talking about, I happen to have it right here. And I bought this, by the way, immediately after reading American Prometheus, specifically because I heard that this was made into a book.
ah,
But it's right here. It's Enrico Fermi, Nuclear Physics Course Notes compiled by J. Arir, A.H. Rosenfeld, and R.A. Schulter, Revised Edition. But you can look, it's really like old crappy typeset
yeah,
because literally it was notes made at the Manhattan Project, and like a lot of the equations are even handwritten into space and stuff like that. But it's just interesting from a historical standpoint, and he talks about nuclear physics. In fact, if you're interested in that era, there's also Robert Serber's intro. You can find that on the web. Just do a search for Serber, Serber. B is in boy, not V is in victory. So, anyways, if you look for that, it's Robert Serber. He was the assistant to uh, J. Robert Oppenheimer, and he, was sort of like his grad student, if you will. But when all the scientists got to the Manhattan Project, not all of them were from the area of nuclear physics, so we had to give them a primer on how they were making a nuclear weapon. And that lecture is completely available. It's not classified. It was classified for a long time, but now it's not. So you can check that out. I actually find the whole history of making the bomb really, really interesting. I've got a lot of books on it,
it's
read a
crazy.
lot. Yeah, it's wild. It's terrible too. I mean, you made a weapon that killed so
Yeah,
many people, but at the same time, you definitely, as a bare minimum, it made the war shorter.
yeah,
So that helped a lot of lives. But yeah, from an engineering standpoint, it's a very interesting procedure. From a science standpoint, it's a very interesting procedure. So it's just a lot of interesting stuff. Should we have made it? I don't know, but somebody would have. And I'd
yeah.
rather quote unquote the good guys of the time to be the ones that had it than the bad guys. They even talk about Carl's Fuchs, Fuchs. He was the spy that we later discovered was the one that was given Moscow all our secrets.
Yeah.
There's an interesting story about that in Richard Feynman's book, Surely You Must Be Joking, Mr. Feynman, where he's telling about his time at Los Alamos, and his wife has got tuberculosis, and she's in town at basically a medical facility because her condition is so bad. He doesn't have a car because he's only like 17, 16 years old, going through working on his PhD, but going through the Manhattan Project. So he borrows a car from one of the people at the Manhattan Project. The person who loans him the car is Carl Fuchs, the very guy that turns out to be the spy that was stealing everything. So neat little stories of history like that. Let me know if there's anything. In fact, I think I have at the top of this course, I have my other interests, so you can
I've
probably
been
find a
looking at
ton of
this.
titles. You
It's
did
pretty
see
cool.
that?
Yeah, I've been looking through it every now and then.
Yeah, there's a lot of good stuff in there, both history and science and stuff like that. And just over time, when you get 56 years old, like I am now, you sort of look back and say, what's sort of the interesting things of history that keep biting us in the rear and causing
Yeah,
issues. So
yeah.
maybe I better learn something about that.
Oh yeah, I've been really interested into religions lately. I've
Yeah,
been
yeah,
slowly
I still do
trying to,
that myself.
yeah, I've been trying to read all the religious texts and like connect dots and stuff like that. But I
Yeah,
do have a question about the Manhattan Project. I remember there was a part where they said like theoretically when they ignited the bomb, it could,
ignite the atmosphere.
yeah, ignite the. Is that real or like,
Yeah, yeah, that was a real thing, and they literally were not doing the Trinity test until they had a calculation of what the probability of that was, and Ray Robert Oppenheimer had to go on the assumption that okay, it's less than 1% chance. Is that good enough to take the risk? And he said,
yeah.
yeah, so let's do it.
What's crazy about that is because like we're not the only ones now playing with nuclear. I was like, I wonder if someone out like else
It
tries to.
might be doing something that stupid too.
Yeah, yeah. You never know. I don't know. Especially
Yeah,
now, like, whole Iran stuff. Like I don't know. It's crazy.
yeah, I do know that the process that we thought might happen was a real concern. I think we've now determined very definitively, so it's not even 1% chance of that happening. If people go through the same process that we did in developing the two types of nuclear weapons that we currently use, then chances are they'll go through the same checkpoints, and they would probably reach the same conclusions that, oh crap, I might be able to explode the atmosphere by or burn out the complete atmosphere by accident.
Yeah,
But we now have the science that shows that that's not going to happen unless you do something entirely off kilter from the process we went through. It's sort of like if we imagine that Russia was doing creating a nuclear weapon with exactly the same resources we had, and then we were creating a nuclear weapon. We would expect at the end of the day that both groups would have figured it out sort of by going through the exact same paths because there's no inherent reason for Russians to be less intelligent than Americans are. In our case, of course, we had more than just Americans. Oppenheimer was an American, but we had Feynman was an American, but we had Enrico Fermi, who had basically defected from Italy when he won a Nobel Prize and came to America, and he was one of our scientists that was doing the large part of the science. He was reporting back and forth with J. Robert Oppenheimer and the people at there, which meant Hans Bethe and all these other people, and those were from all over the world. We had people from Germany that had defected. We had people from Austria that had just ran away from Hitler and all those sorts of stuff like that. People from
yeah.
Poland. But yeah, it's a neat, interesting thing. Lately, I've been more interested in the electricity and magnetism aspect, so that's why you see those books on Maxwell. But those are fun too, so check them out anytime.
Cool. Appreciate it.
All right, well, have a good one, Michael.
Yep.
Appreciate
Well,
talking to you, and let me know if you need anything. And remember, we always have these times as well as 5:30 to 7:40 Monday through Thursday, right about 7:35 if you show up, no matter if it's your class or not, because it could be on Tuesday and Thursday instead of Monday and Wednesday. Then you just show up, and you can ask me questions as an office hour then too.
okay. Sounds
All right,
good.
all right. See you, Michael. Have a good one.
Thank you.
You're welcome. And I guess that's about it. We've now seen lab module, what week four lab module, which starts with linear graphing one. Of course, you can see on Thursday we're going to do linear graphing two, and that should be it. Hope everybody is now ready to do that lab and complete it and can complete it as explained in the video. Have a good day. Bye bye.